GCE Advanced Level Chemistry Practical Series, experiment number 12, showing the presence of nitrogen in air by an experiment. The aim of this practical is mentioned here, students. So the aim of this practical is to demonstrate the reactions of magnesium with air and formation of magnesium nitride. Now everyone, when it comes to magnesium, if you burn magnesium in air, we immediately think magnesium will only react with oxygen. But apart from oxygen, magnesium can react with nitrogen as well. So this particular experiment is designed to show that magnesium reacts with nitrogen. Apart from just reacting with oxygen, magnesium does react with nitrogen. So this practical is designed to show magnesium does react with nitrogen, and therefore nitrogen is present in the atmospheric air. Introduction. Air that we breathe is a mixture of several gases. The main constituent in air is nitrogen, which contributes to about 79%, while oxygen is the second most abundant with nearly 20% of abundance in air. The rest of the gases, such as carbon dioxide, other inert gases, contribute for less than 1% of air's contribution. So majority of air that you breathe in is nitrogen. Then oxygen. The other gases like carbon dioxide, inert gases like argon contributes for less than 1% of the composition of air. So let's take a look at the percentages of each gas present in air. So this slide indicates the volume percentage of each different gas that we have in air. So air is a mixture, or we can even consider air to be a solution. So majority of the air is going to consist of nitrogen. 78.8% of air is nitrogen. And when it comes to oxygen, 20.95 is oxygen. And then the highest percentage of gas that is present in air is not going to be carbon dioxide, although you may assume that it is carbon dioxide. Then we have argon. In the third position, we have argon. Argon has the highest volume percentage compared to all the rest of the gases like carbon dioxide, neon, and helium. The highest volume percentage is nitrogen, then oxygen, then argon. After that only you will have carbon dioxide with a volume percentage of 0.036, then 0.002 for neon, and 0.005 of a volume percentage for helium. So please keep in mind these percentages. You don't need to remember the exact values when it comes to the last few gases that we have mentioned here, but you do need to remember the volume percentage of nitrogen and oxygen, and you do need to remember the order of the highest volume percentages of different gases that we see over here. The highest volume percentage is seen in nitrogen in air, then oxygen, then not carbon dioxide. Then in third position we have argon. Argon has the third highest volume percentage, and then carbon dioxide. So do keep that in mind. Now students, we come to talk about the chemicals and the equipments we will be using for this experiment. When it comes to this experiment, we will be needing magnesium strip as our chemicals, or one of the chemicals we'll be needing is magnesium strips, Nessler reagent, and then we need red litmus paper. Apart from these chemicals, we'll be needing these equipment as well. A crucible with a lid, clear triangles, droppers, glass rod, Bunsen burner, a pair of tongs to handle the really hot objects that we will be using in this experiment, and sandpaper and a tripod. Now out of these, crucible with the lid and clay triangle will be made of ceramic. Now, we use a crucible, students, whenever we need to provide a high amount of heat to any material. So, in this case, we will be subjecting magnesium strips to really high temperatures, and that can be done with the use of a crucible. And this crucible should have a lid, otherwise this particular practical that we are talking about cannot be done without a lid on the crucible. You will see why that is in a moment. So we will need a crucible with a lid, and you need to know we will be using crucibles when it comes to providing a really high amount of heat to some material. You cannot use a boiling tube or a beaker to carry out this experiment, simply because boiling tube or beakers or any other glassware are not designed to withstand really high temperatures, but ceramic materials or ceramic equipment like the crucibles we have over here can withstand really high temperatures. So we will be using a ceramic crucible with a lid for this experiment. And to hold the crucible while it is getting heated, we will be using a clay triangle. So the clay triangle is used to properly place and hold the crucible while it is being provided with a really high amount of heat with the use of a Bunsen burner. Now let's move on to the next slide. So this is our setup, students. We have over here our crucible supported by a tripod, and on the tripod we have our clay triangle, and clay triangle is used to hold the tripod here. Otherwise, if we use a wire mesh, it is not going to be able to withstand the really high temperatures that we will be subjecting this crucible to for a very prolonged period of time. So therefore, we will be using a clay triangle instead of supporting this crucible with a wire gauze. Apart from that, we need to close this crucible with its lid. In this particular experiment, we need to make sure that the contents within the crucible are not exposed to air. So therefore, we need to have the lid on the crucible. Lid is an essential item here. It is not optional. Lid is a must-have in this experiment that we are conducting. So we have pieces of magnesium strips included in the crucible at this point. We will move on to a much clearer image of this over here. What we have here is a clay triangle. There are 3 metal wires, and then we have small clay cylinders in the 3 metal wires that are providing us with an opening over here to place. This is the top view of a clay triangle. So we have an opening here where we can slowly place our crucible into. So to this opening we can place the crucible and we can use this clay triangle to hold the crucible in place. So what we have over here, I will first draw our arrows, it will be easier. We have our tripod here. This is the clay triangle side view. This is the clay triangle top view. Both of them are clay triangles. And we have the crucible lid here. This would be our crucible. And what you have over here is the magnesium strips. And we have a Bunsen burner providing heat. So the first arrow I drew was pointed at our tripod. This is our tripod. Our clay triangle is here. This is the top view of the clay triangle. We have the crucible lid. And this is the crucible. we have our magnesium strips and the Bunsen burner. So students, this is the setup we will be using for our experiment. We will place our magnesium strips here and we will have a crucible where the lid is going to be placed on the crucible after we place the magnesium strips inside the crucible. So, and then the crucible is going to be placed on top of our clay triangle. So let's move on to the next slide. So let's take a look at how we conduct this experiment. Since different chemical compounds can be formed on the surface of magnesium metal strips, it is not observed to be shiny. Therefore, first of all, we will remove the bonded material from the surface of the magnesium strip with a sandpaper to make it a shiny metal surface. So the very first step, students, when it comes to working with magnesium for any reaction is to sand down the outer coating of the magnesium strip. Magnesium strips usually come with an outer layer of coating. This can also get formed when you leave magnesium strips exposed to air. It will react with oxygen to form a magnesium oxide layer. So what you see on the outermost surface of magnesium is not magnesium. There is going to be either a coating of different materials to protect the magnesium from reacting with oxygen, or majority of the time what you are going to observe or magnesium oxide formed that is going to be present on the outermost surface of magnesium strips. So students, when you're working with magnesium, the very first thing we do is we remove the magnesium oxide that is found on the outermost surface of magnesium strips. So to do that, you can take a sandpaper and then we can sand down the outer surface until the outer layer is completely removed, and at that point, when the outer layer is completely sanded down, it will reveal the magnesium metal. Magnesium metal has its metallic luster, so the shiny metal that reveals itself is going to be an indication that you have sanded down the outer layer to reveal or to expose the magnesium metal. So at that point, if you have evenly sanded down the entire magnesium metal strip, you can take that for our experiment that we will be conducting today. After cleaning the magnesium strip, you have to cut the magnesium strip into small pieces and then you have to place it in the crucible. After placing the magnesium strips in the crucible, you have to close the lid and then heat it for about half an hour. You are not supposed to open the lid while heating. The main purpose of closing the lid and conducting this experiment is to ensure that magnesium mainly comes into contact with nitrogen. Magnesium has more of a proclivity to react with oxygen to form magnesium oxide. However, when we heat the magnesium strip in a closed container, initially the small amount of oxygen that is present within that container or within the air volume that is contained in the crucible is going to react with the magnesium strip. So after oxygen concentrations go down, it will start to react with nitrogen. If you open the lid, you will reintroduce a fresh volume of or new volume of air into the crucible, which will introduce more oxygen into the crucible. At that point, magnesium will again prefer to react with oxygen, so therefore magnesium will mainly end up reacting with oxygen. So as this reaction proceeds, it is not advised to open the lid when the reaction is taking place. So until all the magnesium has reacted with the air within the crucible. You are not supposed to open the lid on and off and introduce some more oxygen into the crucible. So when all of the oxygen inside the crucible runs out, or when the oxygen concentrations come down significantly, at that point magnesium will mainly react with nitrogen to form magnesium nitride. So we need to produce magnesium nitride to prove that nitrogen is present in atmospheric air. So in order to produce magnesium nitride, as I mentioned earlier, when you are carrying out this experiment, crucible lid is essential, because crucible lid will provide us with the opportunity to produce an enclosed environment within the crucible. So within this enclosed environment, you have a limited number of oxygen. After oxygen runs out, it will start to react with nitrogen. Here in the crucible, magnesium metal reacts with oxygen and nitrogen in the air to form magnesium oxide and magnesium nitride. Magnesium oxide is formed when the temperature is around 600 degrees Celsius, and magnesium nitride is formed when temperature is around 700 degrees Celsius. Magnesium reacts more readily with oxygen gas than nitrogen. So that is why we keep the lid of the crucible closed. Magnesium reacts more readily with oxygen than nitrogen gas. So the lid should not be opened during heating. Here the magnesium metal reacts with the oxygen in the crucible and reacts with the remaining nitrogen gas to form magnesium nitride. We saw the nitrogen percentage in air is extremely high compared to the percentage of oxygen in air. So oxygen will eventually get used up as it reacts with magnesium, and we will have abundant amount of nitrogen within the crucible. So therefore magnesium will start to react with nitrogen to form magnesium nitride. However, the temperature requirement must be met. Nitrogen will react with magnesium only around 700 degrees Celsius or above. If the lid is left open, the magnesium metal is readily converted into magnesium oxide, as magnesium has more of a preference to react with oxygen. Or we can say magnesium reacts readily, more easily with oxygen compared to magnesium reacting with nitrogen. Magnesium does not easily react with nitrogen. You can see over here, even the temperature that we need to produce magnesium nitride is higher than the temperature we need to produce magnesium oxide. So if you leave the lid open, you can be sure that it is going to react more with oxygen. So therefore the main product is going to be oxygen. There's going to be only a very small, extremely small amount of magnesium nitride produced. A majority of the product is going to be magnesium oxide. Now students, what you have over here is another method that we can use to carry out this experiment. So in this experiment, we will be taking the magnesium strip and we will be igniting the magnesium strip by providing it with heat with the use of a Bunsen burner. And then soon after it starts to burn, we will be placing the magnesium strip inside a crucible, and then we will close the crucible with a lid, and we will provide the crucible with some additional heat with the use of a Bunsen burner as well. So we will allow this reaction to continue until magnesium reacts with oxygen and nitrogen to form both magnesium oxide and magnesium nitride within the crucible. After we have conducted this experiment, we will allow the crucible to cool down to room temperature, and then we will take the product. Product is going to be a mix of magnesium oxide and magnesium nitride. We will take the product and we will add some water to the product in the crucible. At that point, students, as soon as you add water, you will observe a gas that is evolved. So you can bring a Nessler reagent soaked filter paper close to the gas that is getting evolved from the crucible. So as the gas comes into contact with the filter paper soaked in Nessler reagent, you will see that this particular filter paper soaked Nessler reagent is going to turn brown. The filter paper is going to turn brown because it is soaked with Nessler reagent. If Nessler reagent comes into contact with ammonium ions or ammonia, what is going to happen is Nessler reagent is going to turn brown. So when you took the crucible, when we added some water to the product of the crucible, the gas that was released, when it came into contact with the filter paper soaked in ammonia, the filter paper turned brown. This would indicate that the gas that is released is ammonia. So let's take a look at how that gas was produced. So when magnesium strip is reacted with oxygen and with nitrogen using a crucible, we will have these two products. When magnesium reacts with oxygen around 600 degrees Celsius, we will form magnesium oxide. Around 700 degrees Celsius, magnesium reacts with nitrogen to form magnesium nitride. So both magnesium oxide and magnesium nitride are formed. When you add water to magnesium oxide and magnesium nitride, magnesium oxide will react with water to form magnesium hydroxide. Magnesium hydroxide is not very soluble in water. However, magnesium hydroxide will form when magnesium oxide is dissolved in water. And magnesium nitride, when reacted with water, it will produce two main products, magnesium hydroxide and ammonia gas. Magnesium hydroxide and ammonia gas will be produced. So, to prove that there was this gas containing nitrogen was released from the crucible, we can bring a Nessler reagent soaked filter paper close to this ammonia gas that is released. So as the ammonia gas comes into contact with this Nessler reagent soaked filter paper, the Nessler reagent will turn brown, so therefore the filter paper will appear brown. So ammonia, apart from that, if you bring a wet red litmus, so why do we need to make it wet? Because ammonia is a gas. So to make sure ammonia comes into contact with the red litmus paper, apart from that, ammonia needs to first dissolve in water to form ammonium hydroxide and create a more basic environment. So therefore, when ammonia is introduced to wet red litmus, a blue color will be observed. The red litmus will turn to a blue color. Why do we need to have a wet red litmus paper? Because ammonia is a gas, and ammonia needs to come and dissolve in small volume of water in order to release hydroxide ions and indicate its basic properties. So we have here red litmus, which is wet. So when we hold a wet red litmus paper or damp red litmus paper, the ammonia gas that comes into contact with the red litmus paper will dissolve in the water there and will create a basic medium which will convert the red color of the red litmus paper to a blue color. So red litmus paper will turn to a blue color if you bring a damp or a wet red litmus paper to ammonia. If you bring a Nessler reagent soaked filter paper, or if you directly introduce ammonia gas into Nessler reagent will turn brown. Now, this is a test that can be done to identify the presence of ammonium ions or ammonia. So both ammonium ions and ammonia will answer to Nessler reagent, and we can very clearly see when we hold Nessler reagent soaked filter paper over the gas that is released, the filter paper will turn brown because ammonia will come into contact with the Nessler reagent and it will produce a brown color. In this experiment, it can be concluded that ammonia is formed. Yes. We brought in the wet red litmus paper and Nessler reagent to confirm the presence of ammonia. Therefore, it can be concluded that there is nitrogen in air. So now, students, we can conclude that nitrogen was in air because the ammonia gas was produced when we added water to the product inside the crucible. So what was originally present inside the crucible? Only magnesium strips. And what else was present inside the crucible after we placed the lid on the crucible? What else was present inside the crucible? Apart from magnesium strips, air was present. So whatever the ammonia that got released when water was added to the product came from either the magnesium strip or the air inside the crucible. And we of course know we clean the magnesium strip. There was nothing other than magnesium on the magnesium metal strips we introduced into the crucible. So the only other thing that was present inside the crucible was air. So the ammonia that is released got released due to magnesium reacting with nitrogen in air. So this particular test concludes or proves that nitrogen was in fact present in air, and that is why magnesium reacted with nitrogen, and then when we added water, the magnesium nitride produced released ammonia gas, and we identify the presence of ammonia gas with the use of Nessler's reagent and a damp red litmus paper. So that is how we will prove that there is nitrogen in air. Now in this slide, everyone, we will be talking about how to identify ammonia or ammonium ions. So when we are talking about identifying ammonia or ammonium ions, the first thing you should be thinking of is Nessler reagent. The Nessler's reagent forms a brown color precipitate when it comes into contact with ammonia or ammonium ions. Ammonia or ammonium ions. So ammonia or ammonium ions form a brown precipitate with Nessler's reagent. When you have the ammonia gas released from the crucible, when you bring in a wet or filter paper that is soaked in Nessler's reagent, ammonia gas will dissolve in the aqueous medium there to form ammonium hydroxides, and those ammonium ions also can react with the Nessler reagent to form this brown color precipitate. Now, although you are not required to know the formula of the Nessler reagent or the brown color precipitate, you should know Nessler reagent is a reagent that contains mercury and iodide ions. When it comes to handling anything that contains mercury, you need to be cautious. You should not allow it to come into contact with your skin. Now we come across another very important question here. Explain why the magnesium strip should be cleaned before starting the experiment. Now, one of the main questions sometimes when it comes to your exams they ask is, why do we clean magnesium strips? Or is it going to be okay to take magnesium strips without cleaning when it comes to any experiment? When it comes to mass measurements of magnesium, should we clean the magnesium strips before measuring their mass? So the answer to all of these questions would be you always have to clean the magnesium strips before measuring their mass or before we use it for any experiment. Magnesium slowly reacts with oxygen in air to form magnesium oxide on the surface of the metal. Cleaning the magnesium with a sandpaper should be done to remove the magnesium oxide layer. So students, in the lab, magnesium strips come in a huge magnesium coil, or we call it magnesium ribbons. So if you take a magnesium ribbon, you will observe it is not having any metallic luster. It is a very dull black color layer or a bit of a grayish white color layer that is going to be on top of the magnesium strips. So this is mainly magnesium oxide, or it could be a coating that is applied on the magnesium strip to preserve the magnesium strip. However, when you are using the magnesium strip, you have to always peel that layer off or scrape that layer off by using a sandpaper. So you have to use a sandpaper and you have to clean the surface until you expose the magnesium metal that is present inside that initial layer that you see on the magnesium strip. So otherwise, when you are trying to conduct this experiment, the oxygen and nitrogen gas in air might not be able to come into contact with the magnesium strip, because on the outermost surface there will be a thick layer of magnesium oxide or another protective coating. So to avoid that type of complications, you have to make sure you clean the surface very well so that it exposes the magnesium metal to air. What is the gas released after water is added to magnesium nitride? What are the observations when a moistened red litmus is pointed at it? Or if you bring a wet or damp red litmus paper and hold it against the ammonia gas that is released, then what will happen? As I mentioned earlier, red litmus paper will turn blue. Why is that? So first of all, when water is added to magnesium nitride, you have to always remember ammonia gas is released. And ammonia is a basic gas that could turn red litmus paper into a blue color. Keep in mind, students, whenever you are trying to observe whether a gas is acidic or basic, don't hold the litmus paper directly above the gas that is released. Instead, make sure that the litmus paper is made wet with water. Otherwise, you will not be able to see a proper color change in your litmus paper. The reaction that takes place is a reaction we observed a little while ago. Magnesium nitride reacts with water to produce magnesium hydroxide, which is not soluble in water, or solubility of water with magnesium hydroxide extremely low. And then we have ammonia gas produced apart from magnesium hydroxide being produced. So this ammonia gas that is released is going to be our way of proving that nitrogen was present in atmosphere, because ammonia contains nitrogen, and in this reaction we didn't separately introduce nitrogen into the reaction mixture. It just came from the atmospheric air. Students, let's take a look at this slide. Metal nitrides in S block. So S block contains group 1 and group 2 elements. So elements in the first group, or group 1, will be lithium, sodium, potassium, rubidium, cesium, francium. Among the group 1 metallic elements, only element lithium reacts with nitrogen. So out of the elements that you see in the first group of S block, you will see only lithium will react with nitrogen to form lithium nitride. Sodium, potassium, rubidium, cesium, they will not react with nitrogen to form metal nitrides. So all the other metals will not react with nitrogen to form any metal nitrides. So then we can move on to the elements in the second group. So second group is also still in the S block of elements. So elements in the second group, beryllium all the way to barium, radium, we see all these elements in the second group reacts with nitrogen to form nitrides. You can see magnesium reacting with nitrogen to form magnesium nitride, calcium react with nitrogen to form calcium nitride, strontium react with nitrogen to form strontium nitride, and again barium will react to form barium nitride. So when barium and nitrogen reacts, barium nitride will be formed. So when it comes to group 2 elements, they will react with nitrogen. Group 1 elements, only lithium reacted with nitrogen. All the others did not show reaction with nitrogen to form metal nitrides. However, second group, all the elements react with nitrogen to form metal nitrides. For elements in S block, so when you talk about elements in group 1 and 2 together, or in other words, when you talk about S block of elements, from all of the S block of elements, only these elements that are written down here react with nitrogen to form a metal nitride. So from group 1, we know lithium will react with nitrogen. Will any other group 1 elements react with nitrogen? The answer would be no. Group 2, we have all of the elements in group 2 reacting with nitrogen to form metal nitrides. We saw that in the previous slide. So this is a summary of that. Taking lithium also into consideration, lithium, beryllium, magnesium, all the way to radium, we can see they react with nitrogen to form metal nitride. And then reactions between metal nitrides and water. When water is added to any metal nitride, it forms metal hydroxide with ammonia. So metal hydroxide along with ammonia will be produced. And if you add magnesium nitride to water, magnesium hydroxide is going to be formed, which is going to be mostly insoluble in water. That is why we have the state symbol S. And we have ammonia produced as well. Calcium nitride, calcium hydroxide, and ammonia. Strontium nitride, strontium hydroxide, and ammonia. Barium hydroxide and ammonia will be produced if you introduce barium nitride to water. And the hydroxides of group 2 usually increases in solubility as you go down the group. So magnesium hydroxide is not very soluble, but as you go down the group, hydroxides of group 2 increases in their solubility. So that's why barium hydroxide is quite soluble in water. Magnesium hydroxide is not very soluble in water. So in each of these cases, you can observe that we have produced ammonia gas. And keep in mind, students, when you talk about lithium, lithium is a group 1 element. So it is not going to be a group 2 element. You have to keep in mind, although we list lithium along with all the other group 2 elements here in this particular slide, lithium is a group 1 element, not a group 2 element. So lithium hydroxide is formed along with ammonia. When it comes to all the other nitrides also, the metal hydroxide along with ammonia gas will be produced. Metal oxides, metal peroxides, metal superoxides. Metal oxides, metal peroxides, and metal superoxides. So we are going to take a look at how these metal oxide, peroxides, and superoxides are usually formed. Reactions with elements of the S block can be classified as first group reactions and second group reactions. So we can take a look at the reactions that are taking place in the first group and second group separately. In the first group, lithium, we can see if you take lithium into consideration, the element lithium will react with oxygen to form oxides only. Do we have peroxides or superoxides formed when it comes to lithium? No. Lithium will react with oxygen only to form oxides, meaning when lithium reacts with oxygen, we will only observe the formation of lithium oxide. You will not observe lithium peroxide or lithium superoxide being formed. Elements sodium reacts with oxygen to form oxides and peroxides. So sodium can react with oxygen to form sodium oxide. With one oxygen, two sodiums will combine to form sodium oxide, because oxide ion is 2 minus in charge and sodium is 1 plus in charge. So therefore the formula will be Na2O. So this is the formula of sodium oxide. And then if you have excess oxygen, if you react sodium in excess oxygen, you will see the formation of sodium peroxide as well. So it is not just sodium peroxide that is going to be formed. It will be a mix of sodium oxide and sodium peroxide, but the main product is sodium peroxide. So in the presence of excess oxygen, sodium can react with excess oxygen to form sodium peroxide as the main product, as well as sodium oxide as another product found in the product mixture. So sodium oxide and sodium peroxide will be formed. Sodium peroxide will be the main product. When it comes to potassium, when potassium reacts with oxygen, it forms oxides, peroxides, and superoxides. Oxides, peroxides, and superoxides. So the main product here is going to be superoxides. Main product here is superoxides. So students, keep in mind when you are talking about reacting potassium with oxygen, mainly these peroxides and superoxides will be formed in the presence of excess oxygen. If you have excess oxygen reacted with potassium, you will not only observe potassium oxide, but potassium peroxide and potassium superoxide will be formed. And out of these three products, the main product is going to be potassium superoxide. So if you are wondering what the ion would be over here when it comes to potassium oxide, the ion is O2 minus. O2 minus ion along with two potassiums form potassium oxide K2O. And when it comes to potassium peroxide K2O2, the ion is O2 2 minus. And when it comes to potassium superoxide, we have O2 1 minus ion. So that is why we have KO2 here. So this is the oxide ion, peroxide ion, and the superoxide ion. One of the most other important details that you should pay attention to is that rubidium and cesium at the bottom of the first group react with oxygen the same way potassium does. So lithium only reacted to form lithium oxide, sodium produced oxide and peroxides, and then potassium produced oxides, peroxides, and superoxides. From potassium onwards, we say rubidium and cesium also will react with oxygen if it is present in excess. They will also produce oxide, peroxide, and superoxide. So now if we move on to talk about second group. So in the elements of second group, we have beryllium, magnesium, calcium here given. So when it comes to beryllium, it reacts with oxygen to form only oxides. So beryllium does not form peroxides or superoxides. Even when oxygen is present in excess, beryllium will react to form only oxides. The element magnesium will react with oxygen to form only oxides. Magnesium also only oxides. Calcium also only oxides. So beryllium, magnesium, calcium, the first three elements in the second group will react with oxygen to form only their metal oxides. Beryllium oxide will be formed, no peroxide or superoxide will be observed. Magnesium, no peroxide or superoxide is observed, only magnesium oxide is observed. When it comes to calcium also, we could do the same. You would not observe calcium peroxide or calcium superoxide, only calcium oxide will be observed. When we talk about strontium reacting with oxygen, it's very important. The element strontium reacts with oxygen under high pressure conditions. To form oxides and peroxides, but not under normal conditions. So we can get strontium to react with oxygen to form peroxides. However, can we form strontium peroxide under normal room temperature and pressure conditions? No. We will have to employ high pressure conditions to produce strontium peroxide. Strontium oxide can be produced. However, if you want to produce strontium peroxides, high pressure conditions should be used in order to obtain strontium peroxide. So we saw the group 2 elements were more reluctant to produce peroxides and superoxides. When it comes to group 2, all the way from beryllium to calcium, beryllium, magnesium, calcium did not produce peroxides or superoxides, only produce their metal oxide. Then we have strontium. Strontium also would not produce its peroxide under normal room temperature conditions, room temperature pressure conditions. However, if you provide high pressure conditions, at that point you would observe strontium reacting with oxygen to form strontium peroxide as well. So strontium oxide and strontium peroxide both can be produced under high pressure conditions. If the high pressure conditions are not provided, only strontium oxide will be produced. When it comes to barium, barium is different to strontium. Barium would react with oxygen under normal pressure conditions to form both oxides and peroxides. It will produce both oxides and peroxides under normal conditions if oxygen is present in excess. So when oxygen is present in excess, you would observe barium reacting with oxygen to form both barium oxide and barium peroxide. So if you observe this trend, you would notice as you go down the group 2, it was easier and easier to produce the peroxide of group 2 metals. So the ease with which we produce the peroxide of group 2 metals increased as you went down the group 2. So we have over here barium oxide which was produced with more of an ease compared to strontium oxide. And the first three elements, beryllium, magnesium and calcium, did not produce their peroxides. However, strontium peroxide was produced under high pressure conditions, but the group 2 element that is right below strontium, which is barium, barium produces its peroxide under normal pressure conditions. So with that, we can move on to the summary. which will provide you with a little bit of an understanding about the trend that is observed when it comes to producing peroxides and superoxides of group 1 and 2 elements. So if you consider group 1, you can see this step-like progression. When it comes to lithium, lithium will only produce lithium oxide or oxide. Then we move on to sodium. Sodium produces both oxide and peroxide. Then the next element right underneath sodium is going to be potassium. Potassium produces oxide, peroxide, and superoxide. And from there onwards, everything else produces superoxides as well. So you can see the step-like trend that you can observe here. So lithium only oxide, sodium oxide and peroxide, and then from potassium onwards, everything will produce oxide, peroxide, and superoxide, especially when provided with excess oxygen. These elements from potassium onwards can produce can produce all oxide, peroxide, and superoxides of these elements. So you should be able to remember this easily with a diagram like this. So I hope you remember which elements are going to produce peroxides and which elements are capable of producing superoxides. And with that, we come to the slide we have over here. We have second group of elements, or group 2 elements. So group 2 elements, beryllium can produce only oxides, no peroxides or superoxides. So you see a little bit of an L-shaped trend here. So when it comes to beryllium, magnesium, calcium, they can't react with oxygen to form peroxides and superoxides. They can only react with oxygen to form their metal oxide. Beryllium will form beryllium oxide, magnesium will form magnesium oxide, and calcium oxide. But the remainder of the elements over here that we see, strontium and barium, they can form both their oxide and their peroxide. But keep in mind, students, strontium will form its peroxide only under high pressure conditions. Strontium will only form its peroxide only under high pressure conditions. So students, with that, we have covered all the relevant information revolving around this experiment number 12, which speaks to us about proving the presence of nitrogen gas in the atmosphere or in air. So to go over the summary, what we did here in this part of our experiment was to discuss a theory that was revolving around experiment 12. So in this theory part, we learned that we need to take magnesium and very carefully sand it down to expose the magnesium metal. You should not leave any traces of magnesium oxide on the magnesium metal surface. And then we learned when we are heating the magnesium metal up to react with oxygen and nitrogen, we need to keep the lid of the crucible tightly closed. If you lift it on and off, you will introduce a fresh volume of oxygen into the crucible, which will tamper our results. So when you keep the lid closed, we learned initially the oxygen that is present inside this closed crucible is going to react with magnesium, as magnesium will readily react with oxygen. So the oxygen inside the crucible is going to first react with magnesium, and as oxygen concentrations go down, the nitrogen inside our closed crucible is going to start coming into contact with magnesium at high temperatures like 700 degrees Celsius. It will react with the magnesium. that we introduced and will form magnesium nitride. So the crucible and the heating was mainly done to produce magnesium nitride. So atmospheric air had nitrogen. Now we have incorporated this nitrogen into a compound. So how did we do that? Nitrogen was reacted with magnesium, and then we have it now in a compound, magnesium nitride. And we learned when you take group 2 nitrides or any metal nitride from group 1 and group 2, if you introduce water to these group 2 or group 1 nitrides, what happens? Metal hydroxide along with ammonia will be produced. So magnesium nitride, when reacted with water, will form magnesium hydroxide and ammonia gas. And then we learned ammonia gas can be identified with a damp red litmus paper. Actually, damp red litmus paper will not be a confirmatory test. It indicates the gas that is evolved when we add water to our magnesium nitride is going to be a basic gas, because wet red litmus paper will turn blue. When red litmus paper turns blue, it indicates the presence of a base. So this indicates the gas that is released is ammonia. In your syllabus, the only basic gas you currently learn is going to be ammonia. However, just because the red litmus paper turned blue, you should not take that as the confirmatory test. You can go a step further to confirming that this is ammonia by taking Nessler's reagent. If you take a filter paper and dip the filter paper in Nessler's reagent and then hold the filter paper against the ammonia gas that is released, when the ammonia gas comes and dissolves in the water in Nessler's reagent in the filter paper, it will react with Nessler's reagent to form a brown color precipitate, which will result in the filter paper turning brown. So if the brown coloration is observed, this is a confirmation that the gas that was released was in fact ammonia. And ammonia was produced due to us adding water into the product that was formed inside the crucible. And the product inside the crucible was formed by reacting magnesium with air. So the nitrogen in the ammonia actually got introduced into ammonia because nitrogen was present in the atmosphere. So students, this confirms that in the atmosphere there was nitrogen gas that was first reacted with magnesium to form magnesium nitride, and then when reacted with water, magnesium nitride turned into ammonia, and ammonia was identified with Nessler's reagent, proving that nitrogen was present in air. So this is the main theory part revolving around experiment number 12. So with this information, we can now move on out of our classroom into the lab to actually conduct this experiment. So let's move on to the lab and conduct this experiment. GCE Advanced Level Chemistry Practical Series, experiment number 12, showing the presence of nitrogen in air by an experiment. In this experiment, we aim to show the reaction between magnesium and atmospheric nitrogen and the formation of magnesium nitride. As you know, students, when magnesium is burnt in air, apart from magnesium forming magnesium oxide, it will also react with the nitrogen in the atmosphere to form magnesium nitride. So the main aim of this particular experiment is to show the presence of nitrogen in air by reacting magnesium with nitrogen under special conditions and observe the presence of magnesium nitride that is formed. Now let's move on to the equipment and the chemicals we will be using for this experiment. Now let's take a look at the chemicals and the equipment we'll be using for this experiment. For this experiment, we will be using Nessler reagent. We'll be using a small beaker along with a small dropper. We'll be using magnesium ribbons or magnesium strips. So over here we have a small piece of magnesium that is freshly cleaned, and then we have red litmus paper, and we are going to be using a pair of tongues, a spirit burner, a Bunsen burner, a crucible with a lid, and a clay triangle to hold the crucible in place while we heat the crucible. Now students, as I mentioned earlier, we are trying to show that the atmospheric air contains nitrogen. Around 78% of the atmospheric air is actually nitrogen. Around 21% will be oxygen, and there's going to be another 1% of other gases, inert gases, and carbon dioxide. So in this experiment, we are going to show that nitrogen is present in the atmosphere by taking magnesium, which is a group 2 element. As you know, when group 2 elements are heated in air, they are capable of forming their oxides alongside their nitrides. So if you take magnesium and heat it in the presence of oxygen or in the presence of atmospheric air, you are going to be producing magnesium oxide and magnesium nitride. So to make sure that this magnesium comes into contact with enough nitrogen and not only oxygen, we are going to conduct this experiment in a small crucible. So we will be having a piece of magnesium here. Ideally, you will be heating the crucible while the magnesium pieces are inside the crucible. And as you know, there will be a limited amount of oxygen. And as it runs out, the nitrogen will have a better chance of reacting with magnesium, producing magnesium nitride. Now, in our experiment, we will light this piece of magnesium. We will heat it until it ignites, and we will introduce it into this crucible, and we will close the lid, and we will allow the magnesium to react with the remaining amount of oxygen in this crucible, and then start reacting more with the nitrogen inside this crucible, eventually producing both magnesium oxide and magnesium nitride. So afterwards, if you take the white color residue that is formed, and if you dissolve it in water, or if you react it with water, you are going to observe the formation of ammonia. Magnesium nitride, when reacted with water, will form ammonia. Magnesium oxide will turn into magnesium hydroxide, which is not very soluble in water, so it will remain as a white color solid. However, the magnesium nitride will react with the water to produce ammonia, can be identified by the use of Nessler reagent. As you know, Nessler reagent, if you add Nessler reagent to a solution containing ammonia, that particular Nessler reagent will turn into a brown color. It will form a brown color precipitate in the presence of ammonia or ammonium ions. So since magnesium nitride reacts with water to produce ammonia, if you take that solution and if you add a drop or two of Nessler reagent, you are going to observe the brown color precipitate that is usually formed in the presence of ammonia. Apart from that, you can take a small portion of the white residue, dissolve it in water, and take a red litmus paper and observe how the solution that is formed is going to be alkaline. So therefore, the red litmus paper will turn blue when you take a small portion of the solution that is formed when magnesium nitride is reacted with water. You have ammonia formed at that point, so the ammonia solution, when tested with litmus paper, red litmus paper, it will turn to a blue color. Now, without further ado, let's move on and conduct this experiment. Since we know the steps of this experiment, you can expect different observations that we are supposed to be observing in each of these steps. First, let's turn on our Bunsen burner and we can start heating the crucible, and we will then, after the crucible is hot enough, we will then take the magnesium strip and we will heat it up and we will include it in the crucible to see the reaction. Now students, to speed up the reaction, we have started heating up our crucible and we have a speed burner here. We are going to be using that to burn our magnesium strip that we have here. So let's first, we can light our spirit burner, and with the use of a pair of tongues we can take this magnesium strip that we have over here, and now we are going to heat it up. As it lights up, students, we are going to be including it in this crucible and we are going to close the lid. And this reaction will continue to happen inside the crucible. Crucible is still being heated. We can turn off the spirit burner here. And as the crucible is heated while the magnesium piece is inside, two things will happen. Magnesium will react with oxygen to produce magnesium oxide, and with the nitrogen present inside this crucible, magnesium will react to produce magnesium nitride. So let's allow this reaction to happen for a while, and then after the magnesium phase has completely turned into a white color residue, we will take out the magnesium piece and we will observe what happens when we react this white color residue with water. Students, now we have allowed this reaction to continue for about half an hour. We have heated this crucible for half an hour. Let's take this crucible off of this tripod and observe the white color residue that is formed. When you are removing the crucible lid, please make sure to place it on something like a tile, because otherwise if you place it on a wooden table, it will start to burn because the crucible lid is going to be extremely hot. And students, as you can see, inside the crucible you can observe that the magnesium strips that we added are completely turned into a white color residue. If you observe here, it is completely a white color residue. Now you can remove these white color residue. It actually breaks apart when you try to hold them. You can remove this onto a petri dish. After removing this onto a petri dish, we can remove this crucible out of the way along with its lid, because these are still extremely hot. And then we can take this white color residue and continue our experiment with this white residue. Now students, to move forward with the test, we are going to be using a watch glass and we are going to transfer a small amount of this white color magnesium oxide and magnesium nitride residue that you have here onto a watch glass, and you can observe here a white color residue. We are going to add Nessler's reagent to this residue. Now students, as I mentioned earlier, when you heat magnesium strips in a closed environment like the crucible that we used, after the oxygen in that environment runs out, it will start reacting with the nitrogen in that environment to form magnesium nitride. When you react magnesium nitride with water, ammonia will be formed. Now, ammonia can be identified by the use of Nessler's reagent. Over here, we have Nessler's reagent, and we are going to add this Nessler's reagent to our white color magnesium oxide and magnesium nitride residue. So let's take a small amount of Nessler's reagent. As you can see, Nessler's reagent is a clear solution. If you add this aqueous Nessler's reagent, now Nessler's reagent is an aqueous solution, so it contains water. So if you add Nessler's reagent directly to this magnesium oxide and magnesium nitride residue, magnesium nitride will dissolve easily in this water to produce ammonia. So therefore, Nessler's reagent will turn to a brown color precipitate. With ammonia, Nessler's reagent will form a brown color complex which is not very soluble. So it is going to be present as a brown color precipitate. So let's add a few drops of Nessler's reagent to observe if there is a color change. Now let's add a few drops of Nessler's reagent here. As you can see students, when you add Nessler reagent, you can see the formation of a brown color precipitate. You can see the formation of a brown color precipitate. Nessler reagent is a clear solution, but as you add Nessler reagent onto this magnesium nitride, magnesium oxide residue, due to magnesium nitride reacting with water, it forms ammonia and it turns this Nessler reagent into a brown color. Now students, as you can see, we can very clearly observe the brown color precipitate formed due to magnesium nitride reacting with water and releasing ammonia. And as ammonia comes into contact with the Nessler reagent, a brown color complex will be formed which is water insoluble. So you can see the formation of a brown color precipitate. So this is an indication that atmospheric air had nitrogen in it. As magnesium reacted with the nitrogen, it formed magnesium nitride, and when we add aqueous Nessler reagent onto magnesium nitride reacted with the water in aqueous Nessler reagent and released ammonia, and ammonia and Nessler reagent produces brown color precipitate. Now let's move on to testing the pH of this solution. For that, let's take a petri dish and let's add a small amount of our residue. And to this, we will add a small amount of water. Now, after adding water with the use of a stirring rod, we'll mix the residue and the water really well, and we can observe the pH of this solution that is formed with the use of a litmus paper. If the solution is alkaline or basic, this red litmus paper that we have with us, the red litmus paper we have with us should turn blue. As I mentioned earlier also, we have magnesium nitride and magnesium oxide. Of course, when you dissolve it in water, you're going to form magnesium hydroxide when magnesium oxide dissolves in water, but magnesium hydroxide is not very soluble in water. However, magnesium nitride, when it reacts with water, it will form ammonia, which will make the solution alkaline. So let's take this red litmus paper and let's dip it in this solution that we have formed. As you dip this red litmus paper in this solution, you can see the red litmus paper is starting to turn into a blue color. If you keep it in for a while, this blue color will be more prominent. So the solution has started to become basic. The reason for this, as I mentioned earlier, is the release of ammonia gas. Is the release of ammonia when magnesium nitride reacts with water. So students, we have our litmus paper here. Now you can see litmus paper has turned into a blue color. The litmus paper has turned into a blue color, indicating that the solution was in fact basic. With that, we can conclude this experiment. As a summary, we observed that magnesium, when it is burned in air with enough and more oxygen, it will form magnesium oxide and a little bit of magnesium nitride. However, when you heat it inside a crucible, magnesium oxide along with a substantial amount of magnesium nitride will be formed. And when magnesium nitride is reacted with water, or when magnesium nitride comes into contact with water, it will form ammonia. Presence of ammonia can be observed with the use of Nessler reagent. And we took a small sample of the white color residue and we added Nessler reagent. We added Nessler reagent to this white residue, and we observed that the Nessler reagent will turn into a brown color precipitate, or there will be formation of a brown color precipitate in the presence of the Nessler's reagent. So Nessler reagent will only produce a brown color precipitate if ammonia or ammonium ions are present in the medium. In this case, when we added aqueous Nessler's reagent, magnesium nitride dissolved in the aqueous Nessler's reagent or in the water present in the aqueous Nessler reagent and produced ammonia, which eventually led to forming a brown color precipitate. And later on, when we used a litmus paper to observe whether the litmus paper turns blue when magnesium nitride is reacted with water, we in fact observed that litmus paper turns blue in the presence of a solution that is made with magnesium nitride and water. Magnesium nitride, when reacted with water, released ammonia, made the solution alkaline, therefore turned red litmus paper into a blue color. So this proves that we have nitrogen in our atmospheric air. With that, students, we can now move on to questions and other important theory parts revolving around this practical. Welcome back to the classroom, students. So in this experiment number 12, we observed how we can prove the presence of nitrogen gas in the atmosphere. We first looked at the theory parts, then we went into the lab, conducted the experiment, and then here we are trying to discuss some questions revolving around this experiment. Let's take a look at the first question. A piece of pure magnesium was burned in a mixture of nitrogen and oxygen gas. Both nitrogen and oxygen gas was there. The resultant solid mixture weighed 1.8 grams and contained magnesium oxide and magnesium nitride. So the mixture contained both of these. Then the solid mixture was added with water. The precipitate obtained was then heated and only magnesium oxide was produced. So students, whenever you add water or whenever you add magnesium oxide or magnesium nitride to water, the product you produce is magnesium hydroxide. And if you, this is magnesium hydroxide will be obtained as a precipitate. If you keep on heating magnesium hydroxide, it will turn into magnesium oxide. So initially we produced magnesium oxide and magnesium nitride. When you add magnesium oxide to water, it will produce magnesium hydroxide. When you add magnesium nitride to water, it produces magnesium hydroxide as well as ammonia. Produced ammonia will not interfere with the process of obtaining our magnesium oxide upon heating of magnesium hydroxide. The mass of the magnesium oxide produced finally was 2.0 grams. Write the balanced chemical equations for all of the mentioned reactions and then calculate the magnesium oxide to magnesium nitride ratio in the solid mixture obtained above. So let's move on to the first question. Balanced chemical equations for the reaction. We have magnesium reacting with oxygen, producing magnesium oxide. So to balance off the reaction, we will have to add 2 in front of magnesium oxide as well as magnesium. So this is going to be our balanced chemical equation for producing magnesium oxide when burnt in oxygen, when magnesium is burnt in oxygen. Magnesium when burnt in nitrogen produces magnesium nitride, Mg3N2. So you will be needing 3 magnesium, 1 nitrogen molecule to produce 1 magnesium nitride. And when magnesium oxide solid is added with water, you will produce magnesium hydroxide. Magnesium hydroxide is not very soluble in water. You can obtain it as a precipitate. So you can observe whether it is balanced as well, 2 oxygens, 2 hydrogens, 1 magnesium. On both sides you have the correct number of atoms. And when magnesium nitride is added with water, you will get magnesium hydroxide and ammonia. So after writing the equation, we can start balancing the equation. There are 2 nitrogens, so I can add a 2 in front of ammonia. There are 3 magnesium, so I can add a 3 in front of magnesium hydroxide. So when you have 3 magnesium hydroxides, there are going to be 6 oxygen atoms. So I would have to add 6 in front of water to get to 6 oxygen atoms. This would mean there are 12 hydrogens. So let's see if we have 12 hydrogens here. there are altogether 6 hydroxide groups. That means there are 6 hydrogen atoms in magnesium hydroxide here. And over here there are 2 ammonia. Each ammonia carries 3 hydrogens. So 2 ammonia carries 6 hydrogens. So hydrogen number is also balanced there. So this is the balanced equation for magnesium nitride reacting with water. So students, afterwards you can move on to what happens when you heat the magnesium hydroxide. If you take magnesium hydroxide and heat it, it will turn into magnesium oxide. And water, it will be removed as a gas. Water vapor would be produced. So this is the equation that you will get when you write an equation for heating magnesium hydroxide precipitate. Right, students, so that's the first question. And then the second question is to calculate, they ask us to calculate the magnesium oxide to magnesium nitride ratio in the solid mixture that is obtained after the combustion of magnesium piece. So we need to find out the magnesium oxide to magnesium nitride ratio. So how do you find that? How do you find that? Now, we first have to assign values for the magnesium oxide number of moles and magnesium nitride number of moles in order for us to get to the answer. Because when you are carrying out this reaction, when you are burning a magnesium strip in nitrogen and oxygen, both magnesium oxide and magnesium nitride is produced. And we do know the mass of the mixture, right? Magnesium oxide plus magnesium nitride mixture had a mass of 1.8 grams. Now this is a rough way of mentioning what is happening over here. So to be more precise, we can say the number of moles of magnesium oxide is equal to X. Let's say the number of moles of magnesium oxide is equal to X number of moles. And magnesium nitride number of moles is equal to Y. You can write number of moles of magnesium oxide is equal to X. Number of moles of magnesium nitride equals to Y. If that is the case, students, you can then write an expression by using their number of moles and their molar masses. Now, before we go on to the molar number of moles, we can actually calculate their molar masses. So, if you take magnesium oxide, we can calculate magnesium oxide's molar mass. Magnesium is 24, oxygen is 16. So magnesium oxide is 40 grams per mole. Magnesium oxide's molar mass is going to be 40 grams per mole. And what about magnesium nitride then? If you take magnesium nitride, magnesium mass is 24. There are 3 magnesiums, and nitrogen's mass is 14. There are 2 nitrogens. So mass coming from magnesium is going to be 72, and this is going to be 28. So magnesium oxide molar mass is going to be 100 grams per mole. So this is the molar mass of actually magnesium nitride, not oxide. Magnesium nitride molar mass is going to be 100 grams per mole. Now we know the molar mass of magnesium oxide. We know the molar mass of magnesium nitride. Magnesium oxide is 40 grams per mole and magnesium nitride is 100 grams per mole. So after finding the two molar masses out, we can move on to developing an expression between magnesium oxide mass and magnesium nitride mass. So we can write mass of magnesium oxide added with a mass of magnesium nitride should be equal to 1.18 grams. 1.18 grams. The number of grams that were seen in the mixture, 1.8 grams, not 1.18. So always double check the masses in the question. So it should be 1.8 grams. So the mass of magnesium oxide is the number of moles of magnesium oxide, which is X, multiplied by the molar mass of magnesium oxide, which is 40 grams per mole. And when it comes to mass of magnesium nitride, it will be number of moles of magnesium nitride, which is Y, multiplied by molar mass of magnesium nitride, which is 100. When you add them together, it should be 1.8 grams. And if you solve it, it will be 40x plus 100y equals 1.8 grams. We can further solve it to get to 4x plus 10y equals 0.18 grams. We'll say that this is our expression 1. So students, we learned apart from this that in the previous question both magnesium nitride and magnesium oxide produce the same ionic compound when added with what? Magnesium hydroxide. That's a precipitate. So when you take this precipitate and heat it, you get magnesium oxide. So over here, magnesium oxide in the latter part of the question that we saw was due to the magnesium hydroxide that was produced through magnesium nitride, as well as magnesium oxide that was produced through magnesium oxide. If you have X many moles of magnesium oxide, we will draw it in different color so that it will be quite prominent. So if you had X many moles of magnesium oxide in the original mixture of the sample when you burned the magnesium strip, if you had X many moles of magnesium oxide in that original mixture, you will produce X amount of magnesium hydroxide when you dissolve that magnesium oxide in water. If you had Y many moles, we actually considered the number of moles of magnesium nitride to be Y. So if you had Y many moles of magnesium nitride, when you add water to it, the magnesium hydroxide that is going to be produced, the number of moles of it is 3Y. You can see with 1 magnesium nitride, 3 magnesium hydroxides are going to be produced. So with one, if the number of moles of magnesium nitride was Y, number of moles of magnesium hydroxide that is going to be produced is 3Y. So we know the number of moles of magnesium hydroxide is directly equal to the number of moles of magnesium oxide that is produced. So I can write over here X, which is the number of moles of magnesium hydroxide that was there in the medium due to magnesium oxide, and the number of moles of magnesium hydroxide that came into the medium due to magnesium nitride. These are the total number of moles of magnesium hydroxide that are present in the medium now. So if you take this many moles of magnesium hydroxide and heat it, how many moles of magnesium oxide will be produced? The same amount. So X plus 3Y many moles of magnesium oxide is there. And this many moles of magnesium oxide, they say, had a mass of 2.0 grams. So now we can move on to carrying out that calculation. So we can write an expression for the final amount of magnesium oxide that is getting produced when you heat the magnesium hydroxide. And as you saw over here, the magnesium oxide number of moles can be written as 3x plus 3y. So I can write it here. Magnesium oxide number of moles is equal to x plus 3y. Therefore, mass of magnesium oxide produced when heating the magnesium hydroxide is equal to its molar mass, number of moles multiplied by the molar mass. Number of moles is x plus 3y. Molar mass of magnesium oxide we found out earlier, it happens to be 40. And magnesium oxide mass they have already given to us in this particular final step. After converting magnesium hydroxide into magnesium oxide, overall mass of the magnesium oxide produced was 2.0 grams. So using this, we can now produce another equation where 2.0 grams is equal to 40x plus 120y. If you don't want to keep such large numbers in your expression, you can simplify it further by writing. I will like to take the x values over here. I can write 4x plus 12y is equal to 0.2 grams. This could be our expression 2. Now we have two expressions. This is one, the other one is this. So both has 4x in it. It is ideal. We can actually now write expression 2 minus the expression 1. So then what happens is this 4x will cancel off. We can see 4x plus 12y minus our expression 1 is going to be 4x plus 10y. 4x plus 10y is equal to 0.2 from expression 2 and from expression 1 0.18. So when you open the brackets and solve this, it's going to be 12y minus 10y equals to 0.02. And then that means 2y is equal to 0.02 and y at that point is equal to 0.01. So value of y is 0.01. That means the number of moles of magnesium nitride, which was the value y value was magnesium nitride number of moles. So therefore number of moles of magnesium nitride is going to be Y, and that is 0.01. So you can substitute a Y value to 1. So we know 4x plus 10y is equal to 0.18. And 10y is going to be equal to 10 times 0.01. So then 4x plus 10 times 0.01 is 0.1 is equal to 0.18. So 4x is equal to 0.08. At that point, x would be, since these cancel off, x would be 0.02. So we said magnesium oxide number of moles to magnesium nitride number of moles. We said magnesium oxide number of moles were x and magnesium nitride number of moles were y. Now the x value we have obtained it to be, we have actually calculated it to be 0.02. Y value we obtained it earlier, it was 0.01. So what is the ratio between magnesium oxide to magnesium nitride? It was 2:1. So the ratio between the two was 2:1. And this is how we calculate the answer to such a question. Now let's take a look at the second question. Write one reaction each to illustrate each of the following scenarios. So let's take a look at the first question, silver metal reacting as a reducing agent, and the second one is nitrogen gas reacting as an oxidizing agent. So before we move on to the second part of this question, we'll answer these two parts. Silver metal reacting as a reducing agent. So you know, if you react silver metal with chlorine gas, you would see the formation of silver chloride. So we have to balance this equation now, students. You can see there are two chlorines here. To balance the number of chlorines on the right hand side, we will have to add 2 in front of silver chloride, and when you do that, the number of silver solid is also going to be 2. So let's take a look at their oxidation number. Now silver over here is 0, and the chlorine also is 0 in its oxidation state. And if you take a look at silver over here, it is now having a +1 oxidation state, whereas chlorine has a -1 oxidation state. So students, when you observe what has taken place over here, silver has undergone an oxidation, whereas chlorine has undergone a reduction. Chlorine has undergone reduction. It has gone from 0 to -1, whereas silver has gone from 0 oxidation state to +1. So the question asks us to show a reaction where silver metal is reacting as a reducing agent. Now, a reducing agent is capable of reducing other chemical species. So we have over here chlorine that is undergoing reduction when it is reacted with silver. So the chlorine's reduction is caused by silver. So therefore, silver is the one that is reducing our chlorine gas that we have over here. So silver here is a reducing agent. Reducing agent. So in this particular question, it is very clear that silver is reducing chlorine, and chlorine goes from oxidation state 0 to -1, so that is a reduction, and that reduction is brought about by reacting chlorine with silver. So silver is the one that is reducing chlorine gas, and while reducing chlorine, silver undergoes oxidation. So whenever you are asked a question like this, you need to keep in mind a reducing agent undergoes oxidation while reducing some other molecule or ion or atom. So that is something that you need to keep in mind. Then the next one is nitrogen gas reacting as an oxidizing agent. Nitrogen gas reacting as an oxidizing agent. So you have this equation. You can talk about production of ammonia. We have nitrogen and we have hydrogens. There are 3 hydrogen molecules indicated here. When they react, we know that it is producing ammonia. You would have learned this under Haber process. And now if you take a look at the oxidation numbers, we can see nitrogen over here has an oxidation number of 0. Hydrogen also has an oxidation number of 0. And hydrogen over here has an oxidation number of +1. And nitrogen here has an oxidation number of -3. Not -1, -3. So students, you can very clearly see that hydrogen here has undergone an oxidation from 0 to +1. 0 to +1 is an oxidation. So this is an oxidation. And nitrogen, on the other hand, has gone from 0 to -3. This is a clear reduction. This is a clear reduction. So as I mentioned earlier, when a reducing agent reduces another chemical species, we saw the reducing agent was undergoing oxidation. Now, if nitrogen is acting as an oxidizing agent, it will oxidize something else, but nitrogen itself will undergo a reduction. So you can see here, nitrogen is undergoing a reduction while oxidizing hydrogen. So here, nitrogen is acting as an oxidizing agent. So here, nitrogen is acting as our oxidizing agent. Oxidizing agent. So students, you need to be able to identify what a reduction or reducing agent is and what an oxidizing agent is. So you can see here, silver in this particular reaction is acting as a reducing agent. So it is reducing chlorine while silver itself undergoes an oxidation. And here nitrogen is oxidizing hydrogen from 0 to +1, while nitrogen itself undergoes a reduction from 0 to -3. So this is the answer to this question. Now we can move on to the next one. Now let's take a look at the B part of the same question. M is a trivalent metal that reacts with dilute nitric acid to produce ammonia. Produced ammonia will react with the excess nitric acid present in the medium to produce ammonium nitrate. Considering the only other products of the reaction are nitrate of the metal and water, write the balanced chemical equation for the reaction. So this reaction, they say we have nitric acid and we are adding metal M to this nitric acid. So this metal M is going to react. It's a trivalent metal. That means after the reaction, the metal M is going to turn into M3 plus, and ammonia will be formed apart from this product M3 plus. Ammonia will be formed. However, in this particular reaction, students, this is happening in nitric acid medium. So there will be excess nitric acid. So it will react with the excess nitric acid to produce ammonium nitrate. So ammonia is not going to be present in the form of ammonia in this particular medium. It will react with the excess nitric acid to form ammonium nitrate. If there was no excess nitric acid, at that point you will not have ammonium nitrate formed. However, when there is excess nitric acid, at that point ammonium nitrate will be formed. So now we are asked to write the balanced chemical equation. So let's take a look at how we can write the balanced chemical equation here. So we have metal reacting with dilute nitric acid, HNO3, producing M3 plus. Since it's a trivalent metal, we know M3 plus will be produced. Apart from that, ammonia is initially produced. Later on, ammonia will be converted into ammonium nitrate. So the oxidation number of the metal is going to be 0. Over here, when it is turned into a product, which is M3 plus, the oxidation state is going to be plus 3. We can take a look at the oxidation state of nitrogen here. That is going to be plus 5, and oxygen number of nitrogen in ammonia is going to be minus 3. So if you take a look at the differences between the oxidation numbers, so you can see over here, nitrogen in nitric acid has an oxidation number of, or oxygen state of plus 5, and it has turned into minus 3 when this reaction was taking place. This is clearly a reduction, and this process will involve altogether 8 electrons. Why? Because we are changing the oxidation number from plus 5 to minus 3. So if you quickly take a look at why we say there's involvement of altogether 8 electrons, we can display, or we can discuss that using a scale like this. So this is where 0 is, let's say 1, 2, 3, 4, 5. This is where plus 5 oxidation state is. And then minus 1, minus 2, and minus 3. So we were originally here when it comes to the oxidation state of nitric acid, and then we have come all the way down to minus 3 oxidation state. So we have passed 8 places, or 8 oxidation numbers to get to minus 3. So the difference between plus 5 and minus 3 is 8. That is why we say that there's involvement of 8 electrons here. And then we can see that M, or the metal, has an oxidation number of 0, and M3 plus has an oxidation number of plus 3. So this is an increase in the oxidation number. So this is a oxidation. This is oxidation reaction. And this involves 3 electrons. So the number of electrons removed in the oxidation and the number of electrons taken in by the reduction are not the same. So in order to balance this electron release and electron uptake, we need to multiply each of these oxidation reactions and reduction reactions by a specific number to get to the same number of electrons in the oxidation reaction as well as the reduction reactions. So if you multiply this oxidation reaction by 8 and reduction reaction by 3, the number of electrons released and the number of electrons taken in are going to be the same. We consider the oxidation reaction to be releasing electrons. Now it is releasing 24 electrons altogether. When you multiply 3 electrons by 8, it is 24 electrons. And over here in the reduction reaction, we say that electrons are taken in. So over here, 8 multiplied by 3 is going to be 24 electrons. So 24 electrons released, 24 electrons taken in. So electrons are now balanced. So we did this by multiplying each of these reactions by a specific number. So when you do that, students, we can write a final equation like this. So the oxidation reaction should be multiplied by 8. So we have 8m, because oxidation reaction involves M and M3 plus, 8m, and reduction reaction involves nitric acid and ammonia. So reduction reaction gets multiplied by 3. So 8m plus 3HNO3 turns into 8m3 plus and 3NH3, 8m3 plus and 3NH3. Now we are not done yet. This is a step in the process of obtaining the final answer. So the question mentions that M3 plus ions are going to be present as metal nitrate, meaning the final in the final product list, you have this M3 plus ion in combination with the nitrate ions, meaning we form our metal nitrate. So nitrate ion is 1 minus charge. The metal ion here is 3 plus charged. So therefore, students, when you write in the formula, the metal nitrate is going to be MnO3 thrice. So you have to have 3 nitrate ions bonded to 1 M3 plus ion. So this is going to be the formula of our metal nitrate. The question says you form metal nitrate, ammonium nitrate and water. Those are the only products that are formed at the end of this reaction. So M3 plus ion should be represented this way, metal nitrate. So there are 8 M3 plus ions. So then all of these M3 plus ions are going to be present in the form of metal nitrate. So when you do that, we now introduce a new amount of nitrate ions into the balanced equation. So over here, there were only 3 nitric acid, but now this number of nitric acid is not going to be sufficient to provide this many nitrate ions to be bonded to M3 plus ions. So over here itself we have 8 into 3, 24 nitrate ions. We already have 3 nitrate ions represented in this equation. So 3 plus 24 is going to be 27 HNO3. So we can write this second step like so. So this is still not balanced, but we have come a long way in balancing this equation. The only part that is still not balanced is our ammonia, because we do know that this particular reaction produces ammonia, which eventually reacts with the excess nitric acid that is present in the medium, like mentioned over here, right? Ammonia is going to react with the excess nitric acid in 1:1 ratio to produce ammonium nitrate. So we have produced, according to the balanced chemical equation written so far, we have produced 3 ammonia, and the reaction ratio between ammonia and nitric acid is going to be 1:1. So therefore, students, we are going to have 3 ammonia reacting with 3 nitric acid to produce 3 ammonium nitrate. So we can actually change it over here. We can write 3 ammonium nitrate, NO3. Now we have introduced 3 additional nitrate ions into this side or right hand side of our equation. And where do we get nitrate ions from? We get nitrate ions from the nitric acid. When we wrote ammonia as ammonium nitrate, we introduced 3 more nitrate ions onto the right hand side. So that means we need to add 3 more nitric acids over here. So we'll erase 27. 27 plus 3 is going to be 30. So we have 30 nitric acid and 8 M, producing 8 MnO3 thrice plus 3 ammonium nitrate. So the question says, apart from these 2 products, water is also produced, and we would need water to balance the rest of the hydrogens and oxygens. On the left hand side of the equation, we have altogether 30 into 3, 90 oxygens. 30 into 3 is 90 oxygens are present on the left hand side of the equation, or else we can actually look at number of hydrogens here. That will be easier. So 30 hydrogen atoms are found on the left hand side of the equation, but on the right hand side we only have 3 into 4 hydrogen atoms, which is 12. So that means on the left hand side we are missing 18 hydrogens. So if the only other product we can add here is water, to obtain 18 hydrogens we will have to add 9 water molecules. So when you do that, the number of hydrogens are balanced. And to double check if the number of oxygens are also balanced, we can count the number of oxygens here. There are 9 oxygens coming from water. There are altogether 9 oxygens coming from ammonium nitrate as well. And over here we have 3 into 3 9 oxygens. 9 multiplied by 8 is going to be 72. 9 multiplied by 8 is going to be 72, and 72 plus 9 plus 9 is going to be 9 plus 9 is 18. 18 plus 72 is going to be 90. So overall number of oxygens over here is 90, and overall number of oxygens over here is also 90. 30 into 3 is 90. So number of oxygens are also balanced, students. So this is the balanced chemical equation for the reaction that is given in the question. We have 8M reacting with 30 nitric acid, producing 8 metal nitrate, 3 ammonium nitrate, and 9 water molecules. So that is the answer to this question, students. So when it comes to the exam, you will be getting marks mainly only for this balanced chemical equation. The steps you employed will not be awarded marks. However, you need to follow these steps to get to the final answer. So you need to keep that in mind. So let's move on to the next question. Now let's take a look at the third question, students. Emissions from vehicles with internal combustion engines contribute significantly to air pollution. So this question is mainly about air pollution. Considering only these emissions, answer the following questions. First one, name 5 gaseous pollutants. So we do know that through vehicle emissions there are so many gaseous pollutants that are entering the atmosphere: carbon monoxide, carbon dioxide, nitric oxide, nitrogen dioxide, sulfur dioxide, unburned hydrocarbons. So these are some of the pollutants that are entering the atmosphere. So we have named more than 5 there. Name 2 pollutant elements that are emitted. So the 2 pollutant elements that are going to be emitted are carbon and lead. So in vehicle emissions, you have unburned carbon atoms as well as lead, which is going to be considered as pollutants. So the pollutant elements are going to be carbon and lead. Name 2 pollutants that form stable complexes with hemoglobin. The answer to this question is, students, carbon monoxide and nitric oxide. Carbon monoxide and nitric oxide can form stable complexes, very important. It can form stable complexes with hemoglobin. Name 2 pollutants that can cause acid rains. Acid rains can be caused by nitric oxide. Nitric oxide will react with oxygen further in the atmosphere to form nitrogen dioxide. It can dissolve in water to produce nitric acid. Apart from that, we have sulfur dioxide. Sulfur dioxide can further react with oxygen and get further oxidized to form sulfur trioxide, and sulfur trioxide, when dissolved in water, can form sulfuric acid. So these acid rains usually contain nitric and sulfuric acid that are formed through nitric oxide reacting with oxygen and then dissolving in water, and sulfur dioxide reacting with oxygen and dissolving in water to form sulfuric acid. So the answer to this question will be nitrogen dioxide and sulfur dioxide. Name 3 pollutants that can cause greenhouse gas effect. So students, carbon dioxide is obviously one answer there. Apart from that, we have unburned hydrocarbons. So you can name 2 unburned hydrocarbons with 6 and 7 carbon atoms in the carbon chain. State one method that can be used to minimize the pollutant content in the exhaust emissions from vehicles. So this particular question, the answer would be using a catalytic converter. So I just went over the answers to these questions. We will now move on to actually answering them, writing down the answers. So let's take a look at the first question over here. Name 5 gaseous pollutants. Vehicle emissions contain carbon monoxide, carbon dioxide. They can contain nitric oxide, nitrogen dioxide. Apart from that, they can also contain sulfur dioxide. So we have written 5 by now, but we also have unburned hydrocarbons. Unburned hydrocarbons, CXHY. So the carbon number would vary sometimes from 6 to around 10. So all of these are going to be considered pollutants, gaseous pollutants that are released into the atmosphere through vehicle emissions. Carbon dioxide, carbon monoxide. So carbon dioxide here, carbon monoxide here, nitric oxide, nitrogen dioxide, sulfur dioxide, and unburnt hydrocarbons. Name 2 pollutant elements. So we have unburnt carbon atoms or carbon, and apart from that we have lead. These are the 2 elements that can be considered pollutant elements that are emitted through vehicles. Name 2 pollutants that form stable complexes with hemoglobin: carbon monoxide and nitric oxide. Carbon monoxide and nitric oxide is the answer to this question. Name 2 pollutants that can cause acid rain. So we can write down nitrogen dioxide and sulfur dioxide. Nitrogen dioxide and sulfur dioxide, both of these gases can cause acid rains. As I mentioned earlier, when nitrogen dioxide dissolves in water, it can form nitric acid. And sulfur dioxide, when reacted further with oxygen and then dissolved in water, it can form sulfuric acid, which contributes to acid rains. Name 3 pollutants that cause a greenhouse gas effect. So we can write down carbon dioxide, and then we have unburned hydrocarbons like C6H14, C7H16. So these are some of the gases that contribute to greenhouse gas effect, which leads to actual global warming. So these are some of the gases that contributes to greenhouse gas effect. State one method that can be used to minimize the pollutant content in the exhaust emissions from vehicles. So one of the methods that is currently in use is the use of a catalytic converter. You might have seen, students, near the exhaust pipe of a vehicle, there is a small enlarged area that exhaust emission has to pass through before being released to the atmosphere. You might have seen this type of So this area is known as a catalytic converter. Catalytic converter. So the emissions, like especially the toxic emissions like carbon monoxide, nitric oxide, unburned hydrocarbons, carbon dioxide, nitrogen dioxide. So these types of all the emissions are going to first pass through this catalytic converter, and these toxic gases like nitric oxide, carbon monoxide, they are going to be converted into less toxic versions. For example, nitric oxide is going to be turned into nitrogen gas, and carbon atoms or hydrocarbons that are unburned, they are going to be turning into carbon dioxide, as well as carbon monoxide, which is a toxic gas. It is also going to be converted into carbon dioxide. Apart from that, some amount of water will also be produced, especially when unburned hydrocarbons are fully oxidized to form carbon dioxide and water. So these catalytic converters, they contain a ceramic honeycomb structure inside to make sure that there is enough surface area. They have this honeycomb structure inside, and the gases have to pass through this surface area, and the surface of this honeycomb structure is plated with metals like platinum, palladium, rhodium. So these metals are capable of catalyzing reactions to make sure that toxic gases like carbon monoxide and nitric oxide, they react with one another to form less harmful versions of these gases. You know, nitrogen is not harmful at all, but we can say carbon monoxide is quite harmful, nitric oxide is toxic. So these will react to form less harmful carbon dioxide and nitrogen gas. Apart from that, We can also see that when it comes to unburnt hydrocarbons get fully combusted and will form carbon dioxide and water. Carbon monoxide can react with further oxygen as well to produce carbon dioxide. So catalytic converters are usually used in vehicles to make sure that the emissions are less harmful when they are released from the exhaust pipe. And keep in mind, students, when it comes to a catalytic converter, it requires a temperature of about 400 degrees Celsius to properly operate, and that temperature is acquired by these exhaust fumes or exhaust gases. These exhaust gases are coming straight from the internal combustion engine, and the engine heat, or the after the burning of fuel, the type of temperature that is observed in these exhaust fumes are quite high. So that heat will be transferred into the catalytic converter, and the catalytic converter will acquire high temperature. So at that point, these reactions will be effectively catalyzed by the catalysts that are present in the catalytic converter. Metals like platinum, palladium, and rhodium are capable of catalyzing reactions like this. So students, one method that we can minimize the pollutant content that is released to the environment through vehicle emissions is fixing catalytic converters to all the vehicles. So we do currently use this solution. Right, let's move on to the next question. So the next question has a few parts. So we will move on to each part one at a time. So let's take a look at this question. The following questions are based on nitrogen gas, the main component in Earth's atmosphere, and the various compounds that contribute to different environmental issues. The first part of this question: due to the inert nature of nitrogen gas, fixation of nitrogen gas requires special conditions. Explain why nitrogen gas is an inert gas. Now students, nitrogen gas has this Lewis structure. Now you might have drawn the Lewis structure for nitrogen many a times. So this Lewis structure can be used to explain why nitrogen gas is such an inert gas. Two nitrogen atoms are bonded together through a triple bond. There is a triple bond, students. A triple bond is a very strong bond, and breaking this bond and reacting the nitrogen atoms with other chemicals is going to be very difficult. So nitrogen gas is going to be inert because when it comes to reactions revolving around nitrogen, they first need to break this bond to release nitrogen atoms. And this bond is so strong, it requires about 946 kilojoules per mole to break the bond. So nitrogen is inert due to the presence of a very strong bond over here. So it has a really high enthalpy or bond enthalpy here, and to break this bond it requires about 946 kilojoules per mole of energy. So since this is a very strong bond and it requires large amount of energy to break these three bonds, nitrogen is going to be mostly inert. So you can write N2 has a triple bond and to react this bond must be broken. Since the energy required for this process is significantly large. We don't observe reactions of nitrogen under normal conditions. We can say room temperature conditions. So students, this is the answer to that question. So nitrogen has a triple bond and it's quite strong, and since this bond is not easily broken, you don't observe many reactions revolving around nitrogen gas at room temperature. However, we saw when it comes to vehicle emissions, nitric oxide and nitrogen oxide or nitrogen dioxide was a product. So how do we form nitric oxide and nitrogen dioxide in vehicle emissions? How are these gases present in vehicle emissions? Especially in an internal combustion engine, students, we will observe that atmospheric air is taken in to burn the hydrocarbons or to burn the fuel, and this burning takes place in a piston where the pressure is elevated as well as the temperature. So under high temperature pressure conditions, that means those are special conditions, under high temperature pressure conditions, nitrogen gas can react with oxygen to form nitric oxide and nitrogen dioxide. So keep in mind, students, nitrogen gas generally don't react with oxygen to form nitrogen dioxide, especially normal atmospheric temperature pressure conditions. However, inside internal combustion engines, due to the high pressure and high temperature conditions that are going to be observed inside a piston, you will see nitrogen gas will react with oxygen to form nitric oxide and nitrogen dioxide. So those are special conditions, students, and extreme conditions, high pressure, high temperature conditions. At those conditions, yes, nitrogen gas can react with oxygen to form nitric oxide and nitrogen dioxide. State 2, natural processes that carry out nitrogen fixation. So we do see nitrogen fixation happening through atmosphere, through lightning. So we say that is atmospheric nitrogen fixation. And then we have biological nitrogen fixation. Now, biological nitrogen fixation can happen through bacteria. So we say nitrifying bacteria. Nitrifying bacteria can carry out nitrogen fixation. Apart from that, plants with root nodules like legumes and apart from that, legumes and plants with root nodules also can carry out biological nitrogen fixation. State the name of the industrial process that is used for nitrogen fixation. So students, when it comes to an industrial nitrogen fixation, we usually take atmospheric air and then we liquefy it, and through fractional distillation we can get nitrogen. We can separate nitrogen. So after taking nitrogen and reacting it with hydrogen, we can produce ammonia. So this is an industrial process that leads to nitrogen fixation. So this particular process where nitrogen and hydrogen is reacted to form ammonia is known as Haber process. It's also known as Haber-Bosch process. Haber-Bosch process. So if you have written Haber process itself is enough, but the full name is Haber-Bosch process. Identify the two nitrogen compounds that contribute to photochemical smog. We have nitric oxide and nitrogen dioxide contributing to forming photochemical smog, students. So the next question says, explain how these compounds mentioned above contribute to the formation of photochemical smog. So now let's explain how these compounds are going to be contributing to the formation of photochemical smog. So nitric oxide can react with oxygen in the atmosphere to produce nitrogen dioxide, students. So under certain conditions, nitrogen dioxide, especially at temperatures above 15 degrees Celsius when exposed to UV radiation, it can undergo photodegradation to form nitric oxide and atomic oxygen. What we have over here is atomic oxygen. And this atomic oxygen can react with oxygen in the atmosphere to produce ozone. And ozone is a main pollutant. It is a main pollutant. In photochemical smog. It is not the only pollutant, it's a main pollutant, right? So there are other pollutants as well, but ozone is a main pollutant. Now, apart from ozone, this atomic oxygen can react with water as well. Water present in the atmosphere can react with atomic oxygen to produce OH groups or OH free radicals. So these OH free radicals then can react with volatile hydrocarbons. So volatile hydrocarbons are usually denoted by this formula CH3, CH2, N, CH3, where N number is going to be somewhere between 1 to 4. So hydrocarbons with this formula where the N number is 1 or 1 to 4, those are coming under this volatile hydrocarbons category. So those type of volatile hydrocarbons that are present in the atmosphere are going to react with these free radicals to form alkyl groups or alkyl free radicals and peroxyalkyl free radicals. Peroxyalkyl free radicals. So these are alkyl and these are peroxy alkyl free radicals. So these alkyl and peroxyalkyl free radicals will be formed, students, when our volatile hydrocarbons react with these OH free radicals. And we can actually continue on from here directly without writing it again in another separate line. These can react with nitrogen dioxide and oxygen further to produce short chain aldehydes. We can produce short chain aldehydes. And there are two main short chain aldehydes that you should know about. And those are peroxyacetyl nitrate also known as PAN, peroxyacetyl nitrate, and the other one is peroxybenzoyl nitrate, also referred to as PBN. So these two are again main pollutants seen in our photochemical smog. They can undergo polymerization. They actually polymerize. They can polymerize and form small particles, small solid particles in the atmosphere. And these small solid particles are going to be deposited actually these small solid particles can get deposited with dust and water and etc. So dust, water and other pollutants can actually get deposited on these small particles and they can turn into large particles. So a mix of these large particles, these small polymerized particles along with PBN and PAN and ozone, the mix of these chemicals is known as photochemical smog. Students, photochemical smog is the only type of air pollution that we can visibly notice. When there is a photochemical smog in the atmosphere, the large particles found in the photochemical smog will scatter sunlight, so therefore the atmosphere will not appear very clear. The transparency of the atmosphere will go down and it will not appear very clear. So photochemical smog is the only type of air pollution which is going to be very clearly seen. So now students, let's move on to the next part. Identify the two nitrogen-based organic compounds that contribute to photochemical smog. So they're asking for the organic compounds. So we know there are two short chain aldehydes that are containing nitrogen contributing to the photochemical smog, and they are known as PAN, peroxyacetyl nitrates, and PBN. So if you have written these two answers, you will get marks, but you should know what they stand for. This is peroxyacetyl nitrate, and this is peroxybenzoyl nitrate. You should know how to spell them correctly as well. Peroxyacetyl nitrate and peroxybenzoyl nitrate. State 2, adverse effects that are brought about by the photochemical smog. Photochemical smog contains a variety of different chemicals that are harmful to health, and one such chemical is ozone. So ozone can destroy the mucus layer that is found in your respiratory system, which could lead to respiratory complications. And the other pollutants that are there, like particulate matter, we have PBN, PCN, they can also lead to respiratory conditions such as asthma and wheezing. Apart from that, these different compounds in the photochemical smog, especially ozone, can lead to destruction of chlorophyll in plants and damage plant life. It will also slow down growth of plants, and it will reduce the growth as well as the yield of different crops. So ozone is not necessarily good for both the respiratory system as well as plants. So you can write down, we can observe respiratory complications when exposed to photochemical smog, reduction of plant growth, and crop yields. Actually, it can split the double bonds that are seen in rubber, right? So you can write double bonds seen in rubber can be split by ozone. Which leads to reduced mechanical strength in rubber-based products. Reduced mechanical in rubber-based products. Apart from this, we can talk about the fact that peroxyacetyl nitrate and peroxybenzoyl nitrate, PAN, and PBN are carcinogens. They can lead to gene mutation and disruption of enzyme activities. Apart from that, ozone again is capable of acting as a bleaching agent. bleaching agent, which will affect majority of the time to deteriorate, which will bleaching agent. So this can lead to deteriorate the quality of textile products. So this can lead to lowering the quality of textile products. So students, these are the main issues associated with the photochemical smog. So these are the main adverse effects. Respiratory tract related complications can be there. Inhaling the photochemical smog. So photochemical smog not only contains ozone, which is toxic to us, as well as other chemicals such as PAN, PBN, which can lead to conditions like wheezing, asthma, and damaging the mucous layer in the respiratory system, could lead to different types of respiratory complications. Apart from that, reduction of plant growth, and it can affect the yields of different crops as well, because ozone it's very reactive and it can lead to destruction of chlorophyll, which leads to reduction of plant growth and reduction of yields of different crops. And then we have rubber industry can be affected immensely due to the presence of ozone or due to the photochemical smog, because ozone in the photochemical smog can split the double bonds seen in rubber, which will lead to the reduction in the mechanical strength of rubber, and therefore rubber-based products will be affected. And as I mentioned earlier, PAN and PBN are carcinogenic, which can lead to gene mutation and disruption of enzyme activity. Finally, students, since ozone is a bleaching agent, our textile industry can be affected because it lowers the quality of textile products. So students, these are the main adverse effects of the photochemical smog. Identify the main nitrogen compounds that contribute to greenhouse effect. The answer will be N2O. This is the main nitrogen based compound that contributes to the greenhouse gas effect. What are the gaseous nitrogen compounds that cause acid rain? One is nitric oxide, the other would be nitrogen dioxide. So students, nitric oxide will react with atmospheric oxygen to produce nitrogen dioxide. So when you balance this reaction, you will have 2 nitric oxide reacting with 1 oxygen to produce 2 nitrogen dioxide, and we will see 4 nitrogen dioxide reacting with 2 water molecules and 1 oxygen to produce HNO3. You'll be producing altogether 4 nitric acid. So students, this is the reaction that would lead to producing nitric acid. So you can double check whether the equation is balanced. 4 nitrogens here, 4 nitrogens there. We have 8 oxygens here, and then again another 4 oxygens, altogether 12 oxygens. And here we have 12 oxygens, 4 hydrogens here, 4 hydrogens here. This is balanced. So you should know these reactions when going into your test. Nitrogen gas can be produced in the lab through thermal decomposition of certain compounds. Write the balanced chemical equations of the reactions that can produce nitrogen gas through thermal decomposition. So we have ammonium nitrite, NH4, NO2, that can undergo thermal decomposition to produce nitrogen gas and water vapor. Nitrogen gas and water vapor. So this is one reaction, students. So you can see very clearly here, nitrogen gas is going to be produced. Apart from that, another chemical reaction that can be used is ammonium dichromate. And when you do this, you will be producing nitrogen gas along with Cr2, chromium oxide, Cr2O3, and water. So there are altogether 7 water molecules that can actually, 7 oxygens are here on the left hand side, and out of that 3 oxygens are used here, so we are left with 4 other oxygens. So we'll be producing 4 water molecules. To double check whether that is correct, we can take a look at the number of hydrogens here. There are 8 hydrogens here and there are 8 hydrogens here. So this equation is balanced. And students, again, we can indicate the states of each of these compounds. Physical state is solid here, this is gas, and water will also be produced in the gaseous state there. When it comes to ammonium dichromate, that is a orange color solid, and this is going to be produced as a gas, nitrogen gas. Chromium oxide or Cr2O3 is going to be a solid, and this is going to be a gas. If you want to analyze this a little further, ammonium dichromate, if you take ammonium dichromate solid, students, it is going to be an orange color solid, and when you heat this ammonium dichromate orange color solid, it will release nitrogen gas and will produce Cr2O3, and water vapor will also be released. And Cr2O3 that is produced is a green color solid. So you are going to be left with a green color solid, students. So ammonium dichromate is orange, and chromium oxide is going to be a green color solid. So these are the 2 reactions that will lead to producing nitrogen gas through a decomposition of a compound. So now, students, with this we conclude our question discussion. So in the beginning of this experiment, we discussed the theory parts revolving around experiment number 12, and then we went into the lab and actually conducted this experiment, and afterwards we looked at a couple of questions that are revolving around this experiment number 12 as well as nitrogen in general. So I hope by now you have developed a good enough understanding about nitrogen and questions that are revolving around identifying nitrogen as well as nitrogen based reactions. So with that, students, we can conclude this experiment, and I will be seeing you in the next reaction. So see you again in experiment number 13.